hydraulic valve work?
Welcome to Lunchbox Sessions, bite-sized and just what you need. Hello, this is Carl from Lunchbox Sessions.com, and today we're going to be having a look at directional control valves. This will be part 1 of 2 on directional control valve basics. We will be looking at 4-port directional control valves that feature a block P-port when in the center or neutral position. 4-port directional control valves typically have the 4 labels P, T, A, and B. The P-port is for supply from the pump, the T-port
Whoa. Stop listening. I didn't know that's how a hydraulic pump works. It's just 2 gears, star-shaped gears, rotating in opposite directions. And they'll just keep forcing fluid through until something ruptures or something moves. That's incredible. It's cool to know how a hydraulic pump works. I could totally make one. Easily. Well, we'd need to create a hydraulic pump for feeding glue. We'll need to create a hydraulic pump for feeding molten foam, molten glue out of a 3D printer nozzle of a homemade glue-based or epoxy composite 3D printer. We need a hydraulic pump for metering the speed of flow of molten plastic in a machine that converts plastic pellets into thread to use for textiles. Basically a thread creation machine slash plastic recycling machine to create polyester fabric out of water bottles, PET-G, or PET, plastic. Something I have planned to do. I want to create all of my fabric for projects out of water bottles. It's free. That'll be so cool. So that pump will help me with that, knowing how that works. It can be used, oh wow, just using the pump. I could easily create a one-way lift. Just connect the pump, get rid of the directional control valve, connect the pump. If I connected this pump right here, got rid of all the rest, just connected the pump output directly to here, turn that pump on, this piston would freaking push. And that could be used to bend metal or lift a car. Then to pull the piston back, just reverse the direction of the pump. You don't need a directional control valve or a relief valve at all. The only relief that would happen is when we reverse the direction of the pump to relieve pressure, and that would bring the piston back down. So pump direction could just control piston. We don't need valves and stuff. We could just put a pump on every piston. We could fork the pump too. Now a pump like that, what I really like is a pump like this could force air or anything else. It doesn't have to be fluid. It could force air into a cylinder. Boom, we just created an air compressor. That's how easy it is. This would just be open to the open air, and this pump just drives one way. And so you could just have this be an air inlet, and this red line could just run to a container. And as that pump pumps, that container gets air just shoved into it over and over until it's full. And that pump can keep pumping until the container blows up, or pump until the container reaches the PSI we want. That easy. Just two little gears and just a simple little pump. We could create our own compressor. We don't even need a compressor. If we created a pump like this, we could put this red output line directly up to an emergency life-saving small canister, which I could use for kayaking. All I have to create is a little metal cylinder and a one-way valve so I can breathe out of it. And I could just have a little port on it. I could screw my pump up to that port, and it will pump air into this thing until it reaches the PSI I want. And then that will be a couple minutes of air for me to breathe. So you don't need to go to a scuba diving shop to refill a compressed air life-saving device. All you need is a little pump like this, and it will just fill it with compressed air. And you can breathe that air, because that's just outside air. It won't be pure oxygen, but it will be the same air we breathe. And so it's obviously safe to breathe. It's just outside air. And you just force a lot of that into a canister. And that's a scuba diving tank. All you need is this little pump. So that's another application. Another application is you could use this pump to pump air through the nostrils of a humanoid robot and into the body of the robot through a series of tubes. So all the little tubes coming off of here, just picture them just being tubes that just lead to different places throughout a robot. And this pump just keeps turning, and it just forces air through the system. And that air will just distribute itself everywhere. And then you just have a bunch of vent lines running out the other ends of all the little compartments that are getting filled. And those vent lines will let the hot air out as the cool air is forced in. Now, I was planning to create artificial lungs to do that job. But this is another alternative. Just create a plastic geared pump that just moves air. Designed based on this. This pump is so simple. These two little gears turn in opposite directions, and the center of them is always plugged. So as they turn, just the outer sides of them lets air up and around, or fluid up and around. Nothing can get back down. So it's a one-way thing. And if you reverse the direction of the pump, it will suck. So this type of thing you could use, you could use this. Well, like I said, if you connected it to the same part, just one bar of the piston right here, you could have it suck from there or push into there. You don't need two separate lines on a piston. You can create hydraulic or pneumatic, air or oil based. You could push up and down just by reversing the direction of a pump. All a pump has to be is just two little gears and motor to turn it. That's the simplest. I can't believe how simple hydraulics are. It's these big old control valves that are ruining adding complexity and heavy weight. Get rid of that. You don't need it. The control can just be the pump. The pump can just be connected directly to the piston and push it up as the pump rotates one way and pull it down as the pump rotates the other way. That's that simple. I'm blown away. I could really see myself using hydraulics now that I know a simpler way to do it. And one little motor to turn these little teeth is enough to create tremendous force. If these teeth turn long enough, this thing is going to frickin' move. You guys know how strong hydraulics can be. I don't think the motor on the pump has to be that strong. It could be just geared down and just slowly turn these teeth ruthlessly and just build pressure until this thing starts to move, destroying whatever gets in its way. You guys know how strong tractors are and stuff. If I need real power generated in my robot, I could have a little hydraulic pump and hydraulic press, and that thing will push through whatever. And I could put those in the legs. My normal electronic systems and stuff will go until they reach a critical point, and they're just not moving anymore. And then it could kick into gear one of these little pumps, and a little hydraulic motor as a backup system could just go and have the robot push through whatever he's stuck with. Imagine he's doing a bench press and he's stuck. Kick on that hydraulic system, burn, he'll freaking lift anything. That's how we do it. And the hydraulic could just be air. It could just be pneumatics building pressure, pushing with tremendous force. Air buildup could be big just as much as fluid for that type of purpose. And that would get rid of any concerns I've had about hydraulics being, number one, too heavy. Number two, hydraulics being, well, too complex with these valves and stuff. We don't need a valve if we just connect a pump directly to the dang cylinder. That's cutting down the complexity tremendously. No relief valve, none. We're not doing that. So I could really see using that for the robot too. I was going to create artificial heart for the robot, just a sac that opens and closes to push fluid throughout the system, sucking in cool fluid and then pushing it out another valve to push that cool fluid throughout the system, through all the lines under pressure. As the valve pushes, it'll create pressure, and shoving fluid through the system to cool down the system with liquid cooling. Well, I could just create a pump like this instead. Just two little teeth. It's probably maybe a little simpler to make, maybe. I'm picturing connecting one of these cylinders up underneath my bent tie rod with some arms connecting to the bottom of the vehicle, several of them, arms connecting every which way, maybe even bolting this thing into the cement sidewalk in several bolted spots with chains. And then we connect the pump up to this blue part, direct line to the blue, right, this top one, and then we just start driving hydraulic fluid into that, causing this thing to pull. And this thing would be tied off to the tie rod where it's bent. And this thing will keep pulling and pulling, bending the tie rod straight again. Without even taking the tie rod off my car, I can straighten it out that way. With directional pulling with enough force, this would work. I could put a small cylinder or piston with cylinder like this behind my bent body panel, my fender that's bent. Connect a little pump up to this port and have it start pushing, and it could just push the panel, pushing out the bent part. We could just create a short stubby version of this cylinder. Just short and flat and wide, and it could just go and just push out my dent from the inside. Just slide it back there like a pancake shaped thing and just have it push it out. That's incredible. Notice how long and skinny the cylinder is for maximum length? Well, you could create a pancake shaped one. You could create one just this wide that only pushes out a couple inches. And it could just go boom and just push a panel bending it, a bent car panel, to remove the dent. That'd be incredible. I could also use one, a flat squat one, you know, like a pancake. Picture like one of those bowls you store hot taco shells in. Picture that being the shape of the cylinder, just a wide, flat bowl, a couple inches tall, maybe 8 inches in diameter. Maybe only this tall. Or no, it'd be like this tall. You could put a little ramp leading up to it, and then it would lift that high. It could lift your car higher, is what I'm getting at. Well, maybe you could put one under the driveway. Just create a hole in the driveway this big. Make it maybe that tall. And have the cylinder start at the bottom. Or the cylinder head. No, the head of the piston. The piston head's at the bottom and it just lifts. So you could build a car lift into your driveway. It runs flush with the cement. And you can have the top of the cylinder be painted to match the concrete of the driveway. It could be airbrushed and made to look exactly like it. And there'd just be maybe a subtle little line around it, and your dad would scratch his head. That looks a little weird. If you pull your car tires right onto that and press a button, your car just raises up. Would that be incredible? It's a hidden hydraulic lift system built into the cement driveway. I just invented that. That would be awesome. Oh man, you'd never have to drive your car up on ramps or jack up one wheel again. You would just drive the car over it and it'd just lift. That's awesome. Guys, we're doing it, man. We're going to be using this technology right here. But I'm getting rid of the directional control valve. It's not intuitive to me. I like intuitive things. It's so simple just to connect the pump up directly to the piston, and we're go time. That easy. We'll have one pump per piston. No directional control valve. Each piston just has a pump. It's just 2 gears turning, and that's it. We can have as many pumps as we want to connect to as many pistons as we want. All of them lead to the same reservoir. There's no relief valve, there's no release line, there's just a pump and a piston. You either fill it up to the top till it's to the top. You always put the pump at the bottom of the piston. It starts out with the piston shoved all the way in, no fluid. You turn the pump and the piston extends. You turn the pump the opposite direction, the piston comes back. It's now empty. You turn it up, it pushes forward, you turn it back, it pushes back. Changing the direction of the pump changes the flow of the piston. That's it. The pump is just 2 little geared teeth, and that's it. Inside a housing. You can't get any simpler than that. A little pump like this can have one motor control both teeth at the same time. Or it can have one motor on each tooth. The motors would be outside of the housing assembly. A pump like this can determine the flow when extruding plastic through a plastic extrusion machine for recycling 3D printer filament. You always want to push a little more or a little less on that flow in order to maintain the same diameter filament. So this pump could adjust itself based upon a little optical system, just a basic webcam that's just looking really close, zoomed in at the width and diameter of the filament exiting this thing, and the pump could increase or decrease the flow to maintain the perfect uniform filament width. Stop listening. To create the actual piston itself, it's a piston and it's a cylinder, and you could just use pipe. Threaded, wow, just threaded pipe. That's all you need. Threaded black pipe for gas lines for like a water heater. You could just wrap some Teflon tape and screw on a cap on one end, screw on a cap on the other end, and drill a hole through one of the caps, and then just send some steel rod through, matching the diameter of the hole. That end, the top end that we were talking about, that we just drill a hole through, send the steel rod, it's never going to have fluid to come in contact with it, because this portion of the hydraulic cylinder piston head is supposed to be really airtight with the cylinder walls. And in order to do that, it has I think it's just friction fit. It's just pressed in really tight. And it usually has a piston ring applied, like on cars, there's a piston ring. And those can leak over time. So everything's just based on a snug, tight fit, with tight tolerances. So that would be, we would just have to, well, I guess the shaft would be plenty smooth, just buying it stock. I don't know if it'd be smooth enough, but it's supposed to be darn smooth. I don't know if you could put a rubber washer around a piston head and just have that be snug, but then that's rubbing back and forth over time. I guess that would damage it. So maybe a metal washer, and that would just rub back and forth over time, wearing out maybe. But that's normal. You could just put another one on. It's just metal on metal, just scraping. It's supposed to be tight though. How does that work? How could it be tight again? Wouldn't it just scrape? I guess you can rebore. There's a tool that rebores the inside of the cylinder for cars. It's like a sandpaper disc that's pressurized outwardly with springs, and you just slide it down, and then you press a drill, and it just turns, and it sands it all real smooth. So we could put that, a homemade one of those, inside our gas pipeline. And we could use bigger pipe than gas pipe, but I just figure gas pipe's a nice multi-purpose size for a cylinder. And you can go any size, any type of steel piping. You could do like 1/8 or 1/2 inch, 3/4 inch, 1 inch. I can get all that for free too. Just steel or galvanized piping. Black pipe and galvanized pipe. And you just use nipples and put caps on them and drill the hole, and you can make hydraulic cylinders that way. That's amazing. Heck, you could use 1 inch pipe or 1.25 inch pipe of a certain length to create an emergency breathing canister. Wow. That's simple. And then you just fill it with compressed air and put a valve on it, and that valve just leads to a mouthpiece with a one-way valve on it, and you can just breathe right out of that thing. And you just have another valve which you could weld in. You could drill it and then weld it in for applying the pump, which fills it up under pressure. And you could have another valve which you can screw, I guess they're called IPT fitting valves or whatever. You can screw an IPT standard size fitting of a PSI meter, and that way you can turn on your pump as long as you want until it's good, and then you unscrew it and it goes, and then it'll pop off just like a bike tire, and then boom, your PSI says it's full, and you just determine the PSI of the pipe, which I'm sure is rated on black pipe or galvanized pipe. It'll say what PSI rating it can handle before the pipe explodes. And then you can breathe out of that, just a standard plumbing pipe. You could breathe out of it. Rather than buy some fancy scuba cylinder, you could just do it out of a plumbing pipe. That's fantastic. So, applications for robotics. Well, I guess this solves my magic fingers bed idea. I could put just a short flat cylinder under each leg of my bed and put a hydraulic pump. One could lead to all of them, actually. Or maybe one for each. I don't know, because you want the bed maybe to rock around, I'm not sure. And it would just push air in. We could even have a relief valve. It would push air in and then a relief valve with a valved solenoid. A solenoid could open up, relieving this here. So that would just suck a little plunger off of this red line and into the solenoid, and then that would have a spring that would push the plunger back afterward, just like we saw in this solenoid video. The spring would be right here, the inductor right here. So the inductor would kick on, sucking this back, and then the spring would push it back afterward. And so really quickly we could have that push and pull plunger, and this pump could just keep pumping. And that would cause this cylinder, which could just be short and flat and wide, to just go up and down really quick. Basically, we'd create a jackhammer. And that would violently vibrate all four legs of the bed, lifting and dropping the bed, just on a small level. And that would cause the whole bed to become a vibrator. And the idea would be you lay on your bed, and if the whole bed's violently vibrating, it would soothe your muscles. You'd relax, and it would be like a tingly massage. And so that's how I'll do it. I just invented yet another invention or solution. Oh, the applications are just coming and coming. This is technology that, now that I understand it, I have all these projects in mind that I was already trying to solve in my mind that it's instantly solving. So I'm like popping out invention after invention now. If you created a giant-sized pump like this and stuck it anywhere, it would draw air through, correct? Yes. It draws air or fluid through. So I could just create this little pump assembly with a single motor that controls it. And I could... No, I need two motors if it's going to turn indefinitely. A pulley system wouldn't work. Unless if it was a geared pulley that can just turn forever. But, yeah, that's a possibility. But with really big gears, it can move a lot of air. That's the point. So I'd create a big one, like this big, that would draw just a lot of air. And it could draw it through a filter. And that's all it does. It just keeps drawing air through a HEPA filter. And I could air purify my room, getting rid of dust, getting rid of chemicals. It could also have a charcoal filter on it that gets rid of smoke. I could put one on the floor in my dad's office and suck all of his air over time, slowly, but it'd suck all of his air through a charcoal filter that way, as well as a HEPA filter, getting rid of all the crap. I'd love to purify the air in my home. My dad's a smoker, my sister's a smoker, and sometimes it smells like smoke in the basement. Because that air gets sucked through the inlet lines, through the heating system of the house, and then scatters to every room. So the whole house gets an even distribution, so it's not as strong smelling further away, but I'm breathing secondhand smoke all the time. Putting some filters... Well, I mean, I guess I could just put a charcoal filter on the inlet vent of their rooms. But if I put a pump there too, it would permanently always be sucking through it. That's why I'm thinking of that, because otherwise it'd only filter it when the heating system kicks on and it starts pulling from all the air of all the inlet vents of the house. I'd want this thing on all the time. You can see how this same pump, if you put it underneath a big volume of water, like at the bottom of a lake, with a drop off into a river, that this would let the water's pressure would push these gears, letting the water through into the red, and this blue represents the lake and all of its weight, and the red represents where it enters a river. And so over time, the lake water would run around the outer sides of these gears, causing them to turn, And these gears can then be connected to an alternator or a motor, which would cause the motor slash alternator to turn. And that could be a brushless DC motor. And that would produce electricity, which then you could feed into large battery systems to store it, and then an electrical grid. So that's how hydraulic dams work. Same technology as a hydraulic pump or a pneumatic pump. All of it's coming together. I'm seeing how things work. This was kind of a missing gap in my knowledge. I just wasn't really thinking that way. But I just love this concept of a pump connecting to a hydraulic cylinder without the huge control valve. Man, you get 16 hydraulic cylinders and they give you 16 control valves with 16 handles on it like this. And that control valve assembly costs $10,000. You buy it for tractors and whatever. And you can get one that has motors on each of these, and they're huge, and they weigh 1,000 pounds. I'm proposing just a small little pump. Get rid of that. And only have one line on the piston. And the pump can suck out to lower the piston and push forward to raise it. One pump per piston. Get rid of this control valve assembly. These pumps can be small, I bet, too. The bigger they are, the more fluid they'll move with speed. They can be just as strong being small, but they just be slower. So if you want this hydraulic cylinder to move really fast, you just need a bigger pump, so as these teeth turn, it moves the fluid quicker. Although I imagine even a small pump, if it just turns the teeth faster, it would build up pressure just as fast as a big pump. It would just have to be really moving those teeth lightning fast, though. But that'd be ideal, just a really fast small pump. I guess one reason they might have two lines is well, no. I was thinking so that one of the lines eventually comes back to the fluid reservoir. But even with the system I'm proposing, where there's just one pump leading to one line leading to one cylinder, and the line is on the bottom of the cylinder only, the pump would be drawing from the reservoir, coming from the bottom right here, and when it draws the cylinder down, all this red has exited, and then it mixes with cool fluid if the pump's pulling from the bottom of the cylinder, or it'd pull from the top, I guess, so you don't pull debris up with it. So that's not a problem. It's still going to be replacing the fluid with fresh fluid constantly. So no, I can't see a single reason why you'd have two lines. And you know what? I'm sure you can tell me one, but I don't want to know. I think it's simpler just to have one line per piston. The control valve will be electrical, and the control valve is just turning the direction of this pump with a microcontroller. Simple. The motors that turn it. Or motor. In my case, I'm going to have one motor turn it. Just a little output pulley on the motor, and bada bing, bada boom, man. We're golden.